Welcome to the third session of this series of the interactive training in reduction and analysis of interferometric data tutorial, iTrain. Today we are going to learn how to fit interferometric data using the tool UVMultiFit, and the name of the presenter today is Sebastian Müller from the Nordic ARC node.
So we introduced this tool UVMultiFit, which is very good to do this visibility fitting. I will show you how to use it by giving examples and a live demo on a real ALMA dataset. And at the end of the session, we will have a question and answer session. So I will not have time, I will not spend time to explain all the details of interferometry, but I will just set a short background. So interferometer gives us access to the distribution of intensity with spatial frequency of a source. Okay, but we only have, unfortunately, we only have a limited access to this information. So the interferometer gives us only a sparse access to this information from the intensity distribution from the source. And this is what we have in this UV plane here. We only have information from the minimum baselines of the interferometer. Okay, in this case here, 100 meters, up to the maximum baseline, in this case, 13 kilometers. And only a sparse coverage. We don't have, even within this range from the minimum baseline to maximum baseline, we don't have access to all the information. So what we have from the source is an incomplete sampling, and we have to pay the price when we try to reconstruct an image from this. We don't have a perfect image of the source. So the interferometer gives us this information, what we call the visibility, which is measured at each point in this UV plane here. So each point here contains an amplitude, a phase, and a weight. So the visibility is a complex number. And for those of you who are not familiar with this UV plane, it just imagine that you are the source and you are looking at the array, the different antennas, and you're looking how they are projected. And each pair of antennas give you one point in this UV plane. And now, because the Earth is rotating, you see that the point will move in this UV plane here. So now this is information in the Fourier plane, okay? And it's difficult for our mind to understand what is in there. So usually what we want to do is to do a deconvolution to convert this information into an image. And most of the time is done with for example, with a clean algorithm. But what I want to emphasize here is this deconvolution is already an interpretation, or if you want, a model of the visibility data here. And because we have this incomplete sampling, there are some possible artifacts. We have some side lobes in the image plane. Of course, we have a finite resolution. And so what we have in this image now, it's at each pixel noise and intensity. And if you want to characterize the noise in this image, then you will have you have to find a region with no emission, for example, and then you can try to measure a noise. But then you will assume that it's the same noise throughout all the image here. Now, what is visibility fitting or UV fitting? It's just a least square minimization between the observed visibilities that are given by your interferometer and the corresponding visibilities of a source model. So the source model is, you have to choose it. And this is just like a standard chi-square minimization. Okay, so these are the observed visibilities, the model visibilities, weighted by the noise. And this happens in the Fourier plane. So yeah, I know that sometimes it's difficult to understand what is in this Fourier plane. So we need a little bit of gymnastic to see what's happening. So here I just show some examples. So here on the left, you have for a point source in the sky. In the Fourier plane, you will, if you look at the amplitude of the visibilities as a function of UV distance, you will see that they have a constant amplitude. So this is the signature of a very compact point source. So now, for example, if you go to Gaussian, what you will see is for the long baselines, now you will start to resolve the source. And a narrow Gaussian in the sky plane gives you like a broad Gaussian in the Fourier plane. And in the opposite, if you have a broad Gaussian in the sky plane, it will give you a narrow Gaussian in the Fourier plane. So you always have this invert behavior. So this is another example. If you observe a planet, for example, so that the planet can be modeled by a disk, then the Fourier transform of it will be this Bessel function here. And at the place where this function goes to 0, that gives you basically the size of your disk, or it's related to the size of your disk. So just based on the property of the Fourier function here, you can derive properties of the source from the sky. But sometimes, and actually most of the times when you get beautiful ALMA observations, it's possible that this is what you see in the if you look at the visibilities as a function of UV distance. You don't see a real pattern and you don't recognize sources like here. And so this, for example, is visibilities for a nearby galaxy. And this means that the source is too complicated to see a real pattern. And then in this case, obviously, the UV fitting will be impossible to do. So exactly, when should you do UV fitting, or when should you do image your source? So you should do imaging, of course, when for example, when it's the first time that you're looking at an unknown source, you don't know what's going to happen, you don't know what is the source, and of course, you should do an image to see what is there, the first look. And I still encourage you to, even if you know that your source and you know that you can do UV fitting, you still should do an image just in case to see that everything is okay. For complex sources with lots of structures, you have no choice. Then you will have to do an image and work in the image plane because the UV fitting would be too complicated and too many free parameters and too difficult to constrain. On the other hand, you should do UV fitting and those are the best cases when your source is simple and can be described, for example, with an analytical Fourier transform, as I showed you before, a point source, a Gaussian. All these are very perfect sources for UV fitting. If you have good reasons from prior source knowledge, if you know, for example, that it's a lens image of a double quasar, if you know the morphology, the type of your source, for example, if you know it's a planet, then you know that it should appear like a disk. If you have observation at other frequencies or at better resolution, maybe you can constrain. You know that your source should be like this, so you have a good reason and you have good constraints to set a model. And in particular, where your source when the size is close to or smaller than the beam resolution of your observation, and if you have observed with good signal-to-noise ratio, in these cases, then you can maybe retrieve more accurate information from your source than what you could do in the image plane. And other case where you could gain some information from the source by doing some UV fitting, and this is the case when you have a sparse UV coverage. And at the very beginning of interferometry, where they started to try to get observation with only few antennas, or a couple of free antennas maybe, it was basically impossible to make an image, but still they could retrieve some source information from UV fitting. And in case where you have a poor calibration also, then it would be very difficult to do an image, but maybe you could still do something with UV fitting. So what are the advantages of UV fitting and why you should do this? It's because your measurement is done in the UV plane, in the Fourier plane. So this is the natural domain where the measurements are done. So it makes sense to extract information from the measurements in this plane. You can have a quick estimate of source parameters. And for example, you can use this to further self-cal your source. Okay, so maybe instead of trying to make a model out of the visibility, try to do some clean and try to converge to a model. You can already say, if you have some knowledge of your source, you can already start with this model as a first step for self-calibration. So another important aspect is that in the UV plane and with working with the visibilities, you have a robust handling of the parameter uncertainties. And also, if you skip the step to do an image, you remove some potential problems that arise in the deconvolution or imaging process. So this is what I list in this slide now. So there's a lot of things that goes behind imaging. So first, you have to choose a pixel size, which can be arbitrary. So you have good good reasons to choose the pixel size, but this gridding, the weighting scheme, if you want to choose natural, uniform, those are kind of arbitrary and up to the user to decide. The clean deconvolution is a non-linear process. So it means that sometimes strange things can happen. Usually at the end of your deconvolution, you will convolve your image with a clean beam. And if you want to actually measure the size of your source, and if the size is close to the size of the beam, you will need to deconvolve this. So you will need to convolve and deconvolve, which is not really the most efficient way to do. So during the deconvolution artifact, you also have, during the deconvolution, you also can have artifacts. So for example, side lobes or missing flux. If you want to compare different observations, you may have different systematics. So for example, in frequency, if you observe at different time, maybe the UV coverage is not the same. So that's okay. It's easy to see when you are in a UV plane, but if you do an image, maybe you can be biased and maybe you forget this and then make some mistakes. You may have systematics between different configurations, so compact or extended, and of course, between different instruments. Another aspect is that all the pixels within the beam in your image, they're actually correlated. Okay, they are not completely independent. So if you want to study the noise properties, then it's a little bit more tricky because in this case, you have correlated noise. And at the end, when you do this image, as I said before, it's just an interpretation of the visibility data, and it's not unique. You may have some slightly different way to interpret your visibility data. So for example, this is one example in the case where the UV fitting actually can bring you more information than just imaging. And this is observation of my favorite source, which is the quasar PKS 1830, which is actually lensed, and you actually have two different images noted by the cross here. And with this ALMA observation, the resolution was not enough to separate them in the image plane. Okay, the beam resolution is here, so they are not resolved, strictly speaking, in the image plane. So if you want to extract the spectrum from this, you can set at the central pixel here, and this is the spectrum that you will get. So in front of the quasar, there's an intervening galaxy. And in this galaxy, there are some molecules causing molecular absorption, and that's what you see in the spectrum here. So you see these beautiful patterns with different absorption features here. And you cannot say where they come from. But if you make now a model of 2 point sources, so I will say to the visibility fitting, okay, I have one source here, one source here. Please fit my visibilities and tell me what is the spectra, or what is the spectrum toward each of these images. This is what the UVFit exercise will give you. So now you can really separate. And now you see that the red spectrum is actually coming from one source, and the black spectrum is coming from another one. So now you have retrieved this information that was not possible to do this in the image plane because of the marginal resolution. Okay, so now I just want to introduce you this beautiful software, UVMultiFit. So it was developed by Ivan Martividal, who is online with us. Hello, Ivan. It is a very versatile library for fitting visibility data. It works based on Python. And then one nice thing that is that it's easily scriptable. So you have many analytical models available. I will show you in a moment. You can set an indefinite number of source components. You have the possibility to tie parameters of these source components. And you also have the possibility to use frequency dependence through your models. So for example, if you want to do spectral index measurements. So all these things makes it a very flexible and very useful, powerful tool to model your visibility. So if you want to install it, you have the up-to-date instructions in the Nordic ARC GitHub repository here. And you have instruction to install it with Linux or Mac. And in case of any problem, of course, contact us at the Nordic ARC, for example, for help. So here I just show you how to call UVMultiFit. So the most convenient way is to call it from CASA, and you should import it as a library, like import UVMultiFit as, for example, as UVM. And then the way to call it is just like this. So you call it like my fit would be equal to UVM.UVMultiFit with a list of parameters. So the first parameters that you should set is for the data selection, and this is the very standard way. If you have been working with CASA, and for example, ALMA data, you should be very familiar with this. So you just specify what is the measurement set, visibility measurement set. You can select some spectral windows with channel selection, for example. You can select the column, the data column you want to work on. You can select some scans if you want to do, for example, time variability. You can specify the source. Then you can do some on-the-fly averaging in time or frequency here. But at the moment, I will still recommend that you just use one here. And then after, you have to specify your model and the variables that you want to associate with this model. So you have a different model possible. I will show you in the next slides. So you call this just which model you want. What are the variables of your model? You can specify some init guess and so on. And then you have to specify how do you want to have the output of the fit. Okay, and I will show you again later. So here is the list of the available models in UVMultiFit. So basically, it's all a set of models which have easy and analytical Fourier transform, as I showed you before. So okay, you can see the list here. What I want to emphasize is because the Fourier transform is linear, actually you can use combinations of this model. So for example, if your source is best described by a combination of a point source and a Gaussian, then you can decide that your model is this and then fit the parameters as they are. So this is very powerful and very convenient. So for those of you who like the mathematical way of the Fourier transform, here are they. I just basically put them there, and you can refer to this for the definitions later on if you want. And I think we can skip quickly these slides. But here, this is the list of the variable and their properties. So the first characteristic is the position, which is set in UVMultiFit in right ascension and declination as a shift with respect to the phase center. And this shift is expressed in octagon. Okay, so your phase center is the position 0, 0, and all the positions are referred to this position. So the flux is the total flux of the component in Jansky. And for models with an extended size, then you can set major axis, which is the diameter along the major axis in octagons. And you can do two-dimension size, so you can have a major and a minor axis. And the way to set them is just by setting the ratio between the major and minor axis. Okay, and of course you have a position angle, and this position angle is the angle between the major axis, the reference axis, and is from the north to the east in degrees. And if you need if you have models with another size parameter, then it will be described in this sigma additional variable here. For example, in the case of Gaussian ring model. Okay, so let's see how to use this in practice. So this, as a first example, sorry, I show you how to fit a point source with UVMultiFit. So in this case, you will just need to set a model as a 1 delta here. Delta is a name for point source. And the variables will be free. So the position, so they are called like P0. This P is the variable generic name. So the first one, so in Python, it starts as 0. So P0 will be the position in right ascension. P1 will be the offset in declination. And P2 will be the flux density of your source. So you can specify some constraints for these variables. So you can give some guess values. So in this case, I just start the search with a position at 0, 0 and a flux of 1, just to help and guide a little bit the fit, okay? Just in the chi-square minimization. So this is, you can put what you want, but if you put values that are close to what you expect, of course, the fit will converge faster. So just for fit convergence, right? You can also specify bounds for your variables, and it's working for each variable, so you can set the bounds in bracket here. So here, for example, I set for the first parameter, I set please check search, do the minimization only for values between -1 and 1, and the same for the P1 here. And here, for example, I set a constraint that my flux should be positive, so it should be more than 0, between 0 and infinity. And just on the fly, I can give you a good trick if you want to measure the noise level, if you have a non-detection, for example, because I was saying that to measure the noise property sometimes is a few tricky in the image plane, but in the visibility is well behaving. So if you decide to do this with UV fitting, and you just can set, you can fix a source at position 0, 0, but you have a non-detection, so you have nothing in your dataset basically, but you fix a source at 0, 0, and then you search for the flux that it should have. So of course, it should not detect anything, but it will give you the uncertainties, the uncertainty on this flux value, and this uncertainty will give you the 1 sigma noise level for your non-detection, okay? Assuming that it's a point source. And then of course, this is in Gensky, but because it's a point source, then you can set it and say that this is in Gensky per beam in your map. Okay, so now I just want to make it a little bit more complicated, and then just adding another point source. So now we'll try to fit 2 point sources. So now you just specify your model as a list of the 2 components. So the first one, delta point source, the second point source. And now you have to specify the parameters for each of these components. So this is the list as in the previous example for the first source. And then now is the same set of 3 parameters for the second one, okay? And now you have 6 parameters in total. So I set them all 3 parameters, and the fit with the UVMultiFit will fit for all their values. What you can do, as I said, you can tide parameters, and one way to do it, for example, here is to set the first source, point source, which is 3, at 3 position and 3 flux. But you can tie the second one to be at the same position as the first one, but with an offset compared to the first position. So the offset will be P3 and P4 for the offset for the separation in right ascension and declination. And you also can tie the flux by fitting the flux ratio here as P5. Okay. So in this case, I have 2 sources separated by this separation in right ascension declination, P3, P4, and the flux ratio P5. A third example now is fitting a spectral index, for example. So that's the function we would like to fit, the command for the for a spectral energy distribution. So for example, I can choose a model again of a point source. So here I decide that I know the position because, for example, I self-cal and I know the position should be at 0, 0, or I know my source is at position 0, 0. I can fix those parameters. And now I just fit for the flux with a frequency dependence here, okay? So now the parameters of the fit are the flux here, the flux density taken as the reference of 100 gigahertz, okay? So the frequency is expressed in hertz, okay, within UVMultiFit. So P0 will be the flux density at 100 gigahertz. And here in the exponent, the P1 will be now the spectral index. So I can give guess values, for example, a flux of 1 and a spectral index of -0.7, and then just let the fit goes. Just one thing here, of course, you probably need to have a good signal-to-noise ratio in your data, and also a large frequency coverage if you want to be able to really fit correctly this spectral index, of course. Okay, so you have 2 ways to handle the channel selection, and this is defined by the parameter 1 fit per channel. It's just basically the difference between spectral mode and continuum mode. So if you define this 1 fit per channel to be true, then UVMultiFit will do 1 fit to each individual spectral channel in your selection. So that's a spectral mode. Or if you set this to false, then it will fit the whole channel selection at once, okay, as a continuum mode. Okay. And then I want to show you how to output the fit results. So the first thing you can do is specify an ASCII file, and you can do this with this parameter out file, and then you will write the fit results and the models also in this text file here. Okay. And the UVMultiFit is also creating a Python dictionary, which can be called as this variable here. I think I make a mistake here. No, my UVFit is defined as the call to UVMultiFit like this. So now you have this Python dictionary myuvfit.result, and it contains in this parameters section, it contains the fit values. In this uncertainties sections, as it says, is the fit errors. Okay, and you also have some other informations. Then you can retrieve the reduced chi-squared, and you can also retrieve frequency, degrees of freedom. There's a big Python dictionary, and you can have a look if you want. But the most useful values, of course, are here. You also can output fit results directly into the measurement set, and this is controlled by the variable write. So if you don't specify anything, it will not do anything to your measurement set. But you can decide to write the best fit model, which will be saved in the model column, or the fit residuals, which will be saved in the corrected column. So for this, you have to be careful to keep the time width and channel width parameters. They need to be set to 1. Okay, it's just the way to fill in back the information in the measurement set. And if you want to further process these things, so the model or for example, if you want to image the residuals, you have to be careful to use the same data selection, because UVMultiFit is going to fill in this information only for the channels selection and time bin selection that you have been for your selection, right? So if you want to further process, you have to use the same again. So in practice, I think it's a good idea to work on a copy of your measurement set. Okay, otherwise you could overwrite information which are saved in this model or residual corrected columns. So this sometimes you have information from the calibration or self-cal, for example. Maybe you don't want to overwrite this, so yeah, make sure you work on a copy of your measurement set. And then when you do this, then you can directly fit your data in the data column. One caveat is if you don't have a model column in your measurement set, then you will need to create one, and you need to create it by hand, and you can do this using the task for setGenski, for example. But don't, yeah, otherwise UVMultiFit will complain that the model column is not existing anymore. Okay, I would like now to give you one warning about least square minimization. And this is, I think, the standard warning is that you have to choose, of course, a correct model. If you don't do this, then you will always be able to make a fit, but all the fit parameters will be completely crazy if you don't choose a correct model. Okay, and for this, you can guide yourself by looking at the visibilities. And for example, you can plot the amplitude versus UV distance and see if it looks like a reasonable Fourier transform of for example, a point source or a Gaussian or something like this. Or you also can use prior knowledge of the target to guide your fit. So the chi-square minimization is done like this. And in UVMultiFit, it will output the reduced chi-square. So this is the sum. This chi-square is the sum of all the visibilities. Okay, but UVMultiFit will assess on the reduced chi-square by dividing this value by the number of visibilities minus the number of free parameters in your fit. And one important thing is that the final uncertainties on all your fit parameters are obtained from the best fit uncertainties from the Jacobian matrix, but they are rescaled, so that the reduced chi-square, that the reduced chi-square is equal to 1. So this is the standard way to do it, and it's one way to make the uncertainty estimate a little bit more robust, okay, in a statistical interpretation. Okay, so how to judge the goodness of your fit? And that's the tricky part, of course, always when you do a chi-square minimization. So the first thing you can do is check the best fit result parameters, and especially look at their uncertainties. And you should have something that is not completely crazy here. Okay, it should be well determined. You can check the reduced chi-square, and in principle, this value should be relatively close to 1. So if it's much lower than 1, it means that maybe the errors are underestimated in your fit, in your data. And if it's much higher than 1, then it means maybe you didn't choose the correct model for your fit. But maybe in a more practical way or more visual way, you can check the fit residuals. And for this, for example, you can plot the amplitude versus UV distance of these residuals and see if you don't have any systematic in there. You can also make a dirty image of these residuals after you store them in the corrected column. Okay, so you can do this, as I showed you before, you can do this with the right equal residuals parameter. And of course, always keep a critical mind. So you should not forget, for example, as a UV coverage, never forget that you only have constraints between the minimum baselines and the maximum baselines. Okay, so everything else would have to be extrapolated. Okay, so don't forget this. Don't forget you may have some calibration systematics that would not be maybe not properly taken into account by your model, and of course it could affect the goodness of your fit. You may also have some dynamic range limitations. It's also possible that the fit did not converge well, and maybe you are stuck somewhere in a local minimum. So that's why you can use these guess parameters to try to guide your fit and maybe get a robust convergence. And of course, it's not because your fit give you a flux value that is at 1 per mil precision, for example. You should not forget that you may, during the observation, you may have an absolute flux accuracy that is maybe of the order 10 or 20%, I don't know. And this will not be the fitting exercise. Will not, I mean, UVMultiFit will not know what is the absolute flux accuracy of your data. It can tell you what are the uncertainties provided by your data, but if the flux is completely out, then you flip your fit value of the flux will also be completely out. Okay. And for the most advanced and skeptical users, suggest you can try to make simulations, for example, with the OST or with the task SimObserve in Kazaa. And maybe you can try to play with, you can constrain what you put into your simulations and try to play and see what you recover when you do UVFit of them. Just some rules of thumb that I personally find they are very helpful. Is in terms of position measurement accuracy. Typically, what you can achieve by doing this kind of view fitting. So the position accuracy that you can get is the order of the beam size of your observation divided by twice the signal to noise ratio. So you see here that you can beat the resolution that you will get just by doing an image. So the resolution would be the beam full width at maximum. But you can beat or can go a little bit beyond this limit if you have data with very good signal to noise ratio. Okay. And for size measurement, is also a similar constraint. So the accuracy on the size measurement would be the size of your beam divided by the square root of the signal to noise ratio. So for size, it's not going as good as for the position. But still, if you increase your signal to noise ratio, then you will be able to measure, to go beyond the limits of the beam resolution. So you can refer to this publication if you want to learn more about this. Okay, so here are the resources if you want to find information about UVMultiFit. So first, there was a paper published by Ivan presenting the tool and showing the performances and how to use it. So you have information in the Nordic ARC GitHub here, if you want to get the installation. You have a lot of nice documentations in Ivan's personal webpage here. Okay, and you even have embedded into the UVMultiFit distribution, you have what we call a test suite with basically just examples of UVMultiFit fitting, just to check that your installation is correct and that you retrieve the correct, everything that is working in a correct way, well behaving in your computer. Another source of information from UVMultiFit is all the papers, all the publications that have been using it. And I'm very happy that recently the citations on UVMultiFit reached a total of 100 in the ADS. I think it was just like yesterday was the citation number 100. What I want to say is that UVMultiFit is increasingly being used. That's very nice. And it's also covering a large range of science targets. And here I retrieve all the papers citing UVMultiFit into the ADS. I got their titles, and I did this word cloud exercise of the words that are most recurrent in these titles. And you see, not surprisingly, that the ALMA is very recurrent. But you also see a lot of different targets, so galaxies, stars, quasars, gas, jet, okay, and some peculiar objects, disk. So, well, ALMA, UVMultiFit is very well adapted for many, many different science targets. Okay, so now I would like to switch to a live demo. And I have basically 2 exercises to play with you, and maybe we can continue later on in the question and answers. But first, I would like to show you how to fit a model of 2-point sources to real ALMA data of the lensed quasar PK1330. And in the second time, I will show you how to extract the absorption spectrum against these two lensed images. So now I will switch to this. I hope I will not lose you. And I hope we will not get the same problem as before. So I have some instructions here that you can find in the, to try to organize the screens here. Oops. So you can still see the slides, my desktop. Is it okay?
Yes, yes, we can still see it.
So in principle, if you wanted to run the exercises, you should have fulfilled also already these requirements. So to have CASA, UVMultiFit installed, of course, and retrieve the data set at this location. Okay, so the data is just ALMA observation that we observed in 2015. For this data set, I just copy one spectral window, just to make it smaller. So basically, it's the observation of this quasar PK1330, which is lensed, and here you see an image of it. You see two. At millimeter wavelength, you see basically 2-point sources here. So they are very well fitted for very good for UV fitting, 2-point sources. And in front of this quasar, you have a galaxy, and you have absorption from molecular clouds in the galaxy in front of these 2 continuum sources here. So first, I will open the script that we are on the same, and I just will comment the script when I run it. So this is the script as you should get it. Okay. In the same time, so I will open CASA and I will run from CASA. Okay. Okay, so I think you should have maybe basically the same fit as here. So I will call this measurement set here. And the call for UVMultiFit is done just with these lines here. Okay, so here I specify the visibility file. I do some channel selection because first for the continuum fit, I want to avoid some spectral lines. So I set the name of the source. And now here I say my source consists of 2 point sources, so 2 deltas. I set the position here of the first source, and I fit the second one, as I showed you in the example before. I fit the offset, or the separation between the 2 sources, and the flux ratio. And I give this initial guess for the values. So because I want to do it in the continuum mode, I will do this 1 fit per channel. I will set it to false. So again, to switch to all the channel selection will be fitted at once, as it would be a collapsed continuum cube. So the data are stored in the column. The data are stored in the data column. And what we will do is output the residuals after the best fit. They will be written in the corrected column. Okay, and then as an output, or maybe I can run the script when I'm talking. So I can just run it as a standard Python script.
Sebastian, can you bring up the terminal a little bit because it's cut off at the bottom?
This one?
Yeah.
It's okay, better. Thank you. Okay, so I just copy and then just run it as normal way. So it's doing now. And so now UVMultiFit is reading the data. Okay, so just it will take a few minutes at most. And what I do here is I just retrieve the information from the Python dictionary output by UVMultiFit, and I will just print out the errors in a more friendly way like this here. And because I forgot to mention, so after it will just continue and do an image, a dirty image of the source. That's fast. And after the script, we'll also image the fit residuals here. Okay, we can have a look at this after. Okay, so now the UVMultiFit has read the data. Now is fitting the model, and you see the iteration, and you see that the current chi-square, and you see that this value is decreasing. So UVMultiFit is trying to find the best solutions. So the chi-square, note that the chi-square is high, it's because you have a lot of visibilities. So this is not really, let's say, it's difficult to interpret this chi-square value here. And you will see after a more easier interpretation is from the reduced chi-square. So I don't really remember how many iterations, but it should not be so many.
Sebastian, just to remind the participants that since we started a little bit late due to the problem in the beginning, so we are running a little bit late, so we will probably end a little bit later than expected. But anyways, this is being recorded, so then they can always come back to the video that we will upload on YouTube.
Okay.
Yes, and also that all the questions that they're asking, they are being collected in one document, and we will answer them at the end after your presentation.
Okay. Yep. So the exercise actually is a short, so we can do more or go directly to the questions. I think it's the last iteration here. Okay. Anyway, it should be fast after. So I don't know if people are also running in the same time, if they have problems or if it's working. Okay, so now the fit is done, and you see now I print here in a more friendly way the results of the fit. So it found this first source almost close to the phase center with a flux of about 1 Jansky. You see the uncertainty here. And the second source is located about 0.6 arc seconds to the west and 0.7 arc second to the south. Okay. And you see the flux ratio between the two images is 1.5 with the uncertainties. So now it's imaging the data. So it's just is no cleaning there, so it's fast image. and no image the fit residuals, and then we can have a look at this. Once it's done. So again, the fit residuals is just the dirty image, no cleaning. It should be fast. Okay, so then the fit is done, and just give you some numbers here to get the maximum of the image and the noise levels in the residuals, and to get an idea of the dynamic range here. So I prefer to exit CASA, and now to show you, we will have just a quick look at the residual. So I just call CASA viewer for the image here, fit residuals image, and there it is. So in this case, you see that you still have some residual pattern here. Do you see the new window here? Do you see the fit residual here?
Yes, we can see it.
Yes,
Great.
we can see it.
So you see there's some residual thing here. So it means that the cleaning, sorry, not the cleaning, the UVFit model was maybe not totally appropriated, but in this case, it's because the dynamic range is high. So the quasar is bright, and of course, ALMA is very sensitive. And it was prior to a self-calibration. So now, if I put the model, the best model I obtained, and run some self-calibration, and then recalibrate the data with the new gains, then I can do a new fit, and the new fit should be much better than this. But already, if you see, the peak here is already at the level of 1 or 2% already. So just with the data and the first UVFit, you already get to the 1% for the residual, which is already not bad. But the self-cal is definitely improving a lot here. So typically, what you should get in this fit residual, obviously you would like to see only noise in there, and that means that your visibility fitting is well appropriated and your model is correct, and then what is in the residual is just noise in this image. So that would be the best case scenario. And you can also plot your residual visibilities as function of UV distance. For example, with plot MS. I'm not sure I will do it now because maybe I prefer to maybe take more questions. But then it's nice to do this with plot MS, for example, to see if you have systematics with some baselines, for example, or things like this. Okay. So maybe what I can do now is to run the second model, and that actually runs very even much faster. So I will open a new CASA. So I'm always opening CASA and exiting CASA because there could be some memory issues, and sometimes you think that you do correct ways, but then it's just fitting something else that is not because it's something badly handled in the memory. So if you see something strange happening in your fit, I can show you an example while we are talking. Then it's maybe because you should exit CASA and enter again.
Also, in the meantime, if Ivan, if you can hear me, I send you a message in the direct message to a link where we are collecting all the questions. If you can help us, like maybe we can already start answering some of the questions.
Okay, so just briefly now, I just run the second exercise, which is just to fit the two sources that we found before to extract spectra. So now it's doing, and to do this now, now I just turn this 1 fit per channel to true. So now we'll fit all the individual channels, and it will just produce a figure out of this. And the fit should be fast now. I used 2 point sources and I fixed their position to the position we have found before. And now I'm just fitting for the spectrum. So that is the amplitude. So the amplitude toward, okay, that's done already. Okay, now you get the absorption spectra toward the 2 sources. Okay, so this is absorption from the H2O plus molecule. So you find different absorption in front of the two images. So I think the blue one is in front of the southwest source, and the red spectrum here is in front of the northeast. Okay. And just to show you this example of memory leaking, I think if I run it again, so I don't exit CASA, I run it again, the same fit, and you will see. So I'm not sure if it's my computer or, but anyway, you will see the example. Okay, I think I'm done and ready for questions.
Thank you very much for watching. And if you have further questions on how to use UVMultiFit, please contact us via the email address put in the description of this video.